Is it visible? Srishti, are you there? Is it visible? Can you hear me? Hello? Hello? Hello, am I audible?
Hello.
Yes. Am I audible?
Yes, sir. Good evening.
Haha, good evening. Is this visible? This slide?
Yes, sir. It is visible. Yes, sir.
Okay. So we have to wait for another 5 minutes so that other people can join. Okay, then we will proceed. Okay. So wait for
Okay,
another
sir.
5 minutes. Okay.
Okay, sir.
Okay, so now last day I have discussed about some thin film deposition techniques and another technique. So there are pending certain techniques also. And today I would like to discuss another techniques along with some other vapor deposition techniques. We will later on discuss other techniques one by one. Okay, so now there is another technique by which you can deposit thin films. So that is a sputter deposition technique, which was developed by Langmuir in 1920. So it has got certain advantages. Okay. What are those advantages? So sputtering technique will have better step coverage than evaporation. Okay. Addition of magnetic field improves this step coverage. So this is important because uh, you see in case of interconnected metallization, so the surface of the MEMS, if you go machining at the beginning of this process, so then it is not uniform or it is not planar. So there will be lot of ups and downs. So these ups and down means there will be a certain steps over the surface. That is also true in case of VLSI also. Okay, so there is a one demand or need that all the step should be covered by the aluminum or whatever material you are using the material film. so that on the surface you need the planar metal. Okay, so the planarity is another important aspect when you go for deposition of any of the film. So for ensuring the planarity, you have to use certain techniques which cover all the steps. So this is one technique is sputter deposition, by which the step coverage will be better than the evaporation. Okay, it induces less radiation damage than e-beam evaporation technique. So sputtering technique that 10 kilovolt or higher electron beam is not used in this case. So radiation damage is less. That is one advantage. High deposition rate offered by modern design. If you design the sputtering chamber properly, the evaporation rate will be higher. Okay, so that these are the advantage. Other advantages are also mentioned here. Mm, It is capable of uh, depositing, depositing and maintaining complex alloy composition, capable of depositing refractory metals at high temperature, capable of maintaining well-controlled uniform deposition on large wafers. Now, this is the complex alloy composition or refractory metal, because refractory metal capability is one unique thing, because you see the basic principle of the sputtering is the basically you have to create certain ions. The ions will be accelerated there, which is positive ions, not electron beam. So positive ions, uh, why? Because it will uh, have higher mass. If you energize, its impact will be more. Okay, when it hits on the surface. Okay, so as a result of which it will dislodge some of the materials from the target, so that is the basic material, because uh, mechanism of the sputtering. Okay, uh, so now here one point is mentioned, that the alloy composition, you see deposition of maintaining complex alloy composition. So if you make the target beforehand with proper stoichiometric ratio, then uh, if in sputter deposition in the same ratio, the material will come out and it will deposit. But if you go for the electron beam or the resistive heating technique, like I have discussed last day, by using simultaneous evaporation of the material, then controlling of the composition with certain stoichiometric ratio will be difficult. But here, in case of sputtering, the target composition for fixed ratio, fixed composition, fixed stoichiometric ratio composition you can have, and then if you use that particular target, then in the film more or less you can ensure that composition. May not be the exact composition of a target, it depends on the yield of the individual components in the alloy, but you will have better the alloy composition compared to the earlier technique. Okay, uh, other than that, there are other advantages in case of sputter deposition, and they are high energy. uh, Plasma overcomes temperature limitation. That is why you can have the refractory metal evaporation, because refractory metal, if you want to evaporate using the earlier techniques of resistive heat or any other like inductive heat evaporation. I have not discussed the inductive heat evaporation in my lecture. So there is another technique which is inductive heat evaporation. One is resistive heat, another is inductive heat. Okay, so you have to increase the temperature to a high value. Now, because a refractory metals evaporation temperature is very high, melting point is very high. For example, tungsten molybdenum. If you want to evaporate those materials, you have to raise the temperature uh, nearly say 1800 or 1600 degree centigrade. It is very difficult, but if you use a sputter technique, so it is different technique. So they are without raising the temperature to a high value, you can deposit those refractory metals very easily. Okay, now coarse sputtering allows us to control the uh, atomic ratio of the species that I already told you, mentioned in my lecture. So trapping of gas molecules causes anomalies and its mechanical properties. Uh, these 2 points are actually disadvantage of sputtering technique. So one is the trapping of gas molecules, because in sputtering you are using some ions. Now those ions are normally argon ions are used, argon. So in that, in the film, maybe some argon ions will be trapped. So because of the trapping of the argon ions, the property of the film may little bit change. Yeah, mechanical property also may change. And other important point is the stress. So stress is another very important point of thin film deposition, and the stress depends on the specific sputtering condition. That too is very critical to manage in case of sputtering or sputter technique. Okay. So these are the few advantages of sputter deposition technique. Next, so here this is a chamber, sputtering chamber. Here basically, mm, this is the target. Okay,
Yes.
this one, and you see in the top, this is anode where the target is there, and bottom is the substrate holder. Okay, substrate holder. These are the wafers kept, and now these are the vacuum chamber. Okay, this is a vacuum chamber. All this sputtering or evaporation is done in some vacuum. I told you the reason of vacuum using vacuum chamber. Already I have told you the reason. Now if you apply power, so first the one will be the cathode. Okay, another will be the anode. Now since the positive ions were creating, so you have to keep the wafers on the cathode. Okay, another so if you apply certain electric field in between the uh, two plates, uh, argon gas will be ionized. Okay, so this is the inert gas, argon gas will be given, so it will be energized. Now ionization of the argon gas, if the gas inlet is basically we normally use argon gas. So if it is ionized, ionized means the depositive of ion. Okay, positive ion. So obviously if the target is negative, it will basically proceed towards the target. Now if the target is kept negative, so when it will bombard on the target, uh, after bombardment the target material will come out, and since you are keeping the wafers at the bottom, those materials will fall down and it will deposit on the wafer. Okay, so that it's a basic mechanism of the simple sputter system. And one of the limitation here, the particular material to be sputtered is made into a disc or target that is thermally bonded to the cathode. So this is a back plate, is a cathode, and you have to thermally bond the disc here. Now that means source material. If you want to deposit, has to be in the form of the target. No powder, no rod or no plate is used in case of sputter. You have to have certain target, so you have to prepare the target material first, then you can go for the sputter deposition. Okay, so another important aspect is the gap between the cathode and anode. Okay, this gap. So this is less than 10 centimeter. We have seen argon plasma is sustained between the electrodes. Okay, less than 10 centimeter. The closer is the closer the target on the wafer, the higher the deposition rate. Obviously, so if uh, this is the target is close to the wafer, this target is close to the wafer, so higher will be the deposition rate. So these are parameters of the deposition. One is the gap between the cathode and anode. Another is the pressure inside this chamber, vacuum inside this chamber. And another is the ions density. Ions density. Okay. Now that means you have to in some sputter chamber, the plasma, that is the ions, means ion collection of so it's the collection of ions in a system is basically plasma. So confinement of the plasma, argon plasma, is another important aspect. Okay, now if you confine those, so plasma density will be higher. So where the deposition will be more, so that means it depends on many parameters, like the pressure inside the chamber, like the voltage applied, like the physical distance between the cathode and anode. So the deposition rate also will change and quality of the film also will change. Okay, now these are some of the points I just talked, I mentioned here. The gas pressure in the chamber is about 0.1 torr. Okay, plasma chamber is designed such that a high density of ion strikes a target containing the material to be deposited. Now, simple DC sputtering is used for elemental metal deposition and for deposition of insulating materials such as silicon dioxide, silicon nitride, uh, and RF plasma is used because for metal can be used as a cathode. So you can attach with the cathode, but if it is if it is an insulator, then very difficult for DC sputtering because you cannot get the negative field at the insulator. Then you have to go for the RF energy, radio frequency. So for deposition of the insulated material, the DC sputtering is not used. Rather, you have to go for the RF sputtering technique. Okay. Now the next topic is the oxidation of silicon. So this is an important material which is used in case of microelectronic devices as well as MEMS devices. Silicon dioxide is basically a dielectric material which is from silicon reaction with oxygen or reaction with H2O molecules, and that particular material formation is also very easy by thermal technique, and it's a very good microelectronic material, and this particular material is used as a mask against implantation or diffusion of dopant into the silicon. Okay. That means a mask, what is mask means it will prohibit diffusion or implantation in that particular region. Masking, ढके दो. So mask means it will prohibit diffusion or implantation in that particular region. So when you open the windows which the implantation or diffusion will take place, the silicon dioxide is used as a mask. Okay. Second is the isolation among component. Okay. In IC. Uh, uh, that means in integrated circuit, the silicon dioxide is used for isolation because this is a dielectric material. So in between two devices, if you want to isolate, so when you are making the transistors or field effect transistors like FETs or whatever it is, so in between the two devices, if you fill with the silicon dioxide, so automatically they are isolated each other. So it is used for isolation also. The third application is components in MOS structure. That is a gate electron silicon dioxide, which is used as a gate material. That is a component in MOS structure. Okay, then it is isolation in multi-level materialization scheme. In case of VLSI, you maybe know that there are 3, 4, 5, 6, and 7 to 8 layers materialization is used nowadays. So obviously from a small layer to other layer, you have to isolate. So for that isolation, you can use silicon dioxide as a dielectric material in between two metal layers for isolation. So that is one application of the silicon dioxide for multi-level materialization scheme isolation. Then another application is anti-reflective coating for photodiode devices. It has got very good anti-reflective coating, but it can absorb the radiation. So in case of photodiode or in case of other optical devices, it can be used for as an anti-reflective coating. Okay. So these are the various application of silicon dioxide, and there are certain growth techniques of silicon dioxide. One technique is known as native silicon. Now, native silicon dioxide growth, that means if the silicon itself is converted, if it is converted into silicon dioxide, silicon itself, which is to be converted into silicon dioxide, which is known as the native growth of silicon dioxide. Now, locally silicon is converted into silicon dioxide, and that particular technique is very much used because in that technique you can get a very high quality dense silicon dioxide. And there are different techniques of native silicon dioxide growth. These are the techniques. So one technique is known as the thermal oxidation, uh, and there is one is dry oxidation, and where you can use only dry oxygen, and the dry oxygen is reacted with silicon, it will form silicon dioxide. It's known as the dry oxidation. Okay. Second is wet oxidation. There are oxygen species. So oxygen species are the oxygen molecule uh, or H2 molecule. Basically H2 will decompose into hydrogen and oxygen, and the same oxygen will be used for forming silicon dioxide layer. Okay, so dry oxidation, wet oxidation. After that, steam oxidation. Third number is steam oxidation. If you use only H2 molecule as an oxidation species, then it is known as steam oxidation. Here no separate oxygen gas is used. Okay, but if you use combination of oxidation and H2 molecule, then it is called wet oxidation. Okay, next is pyrogenic oxidation. Here basically pyrogenic steam is used. What is that? That is hydrogen and oxygen used separately. Okay, and then it will form the H2O molecule, H2O molecule, and that H2O molecule will act as an uh, uh, oxidation species. Okay, so then what is the difference between steam and pyrogenic oxidation? What is the difference? The difference is in the steam, the water vapor is used, but here the gas is used. Here water vapor is used, here gas is used. Okay, gases are used. The reason is that in water vapor there may be some contamination, but here the high purity gas, hydrogen, oxygen, if you use, there is no chance of contamination. If you use H2O molecule, there is a formation of peats. Okay, because H2O, it can create some nucleation on the surface. So as a result of which there may be some defects and peats if you use high pressure steam. On the other hand, if you use high purity gas of hydrogen and oxygen, and if you form the steam high pure steam inside on the surface of the silicon vapor, then they will form both oxygen and H2O molecule, and they will form native silicon dioxide, and then growth rate will be fast and purity will be high compared to the H2O or H2O steam oxidation or wet oxidation. Okay, so nowadays in most of the cases in VLSI they use pyrogenic oxidation. But only problem is that if you use hydrogen as a separate gas entity, then handling of hydrogen gas is not easy because hydrogen burns itself. And if you use oxygen and hydrogen together to form H2O molecule, so there is a chance of explosion, is not it? So that is why in the total system there should not any leak, and you have to take a great precaution if you use the pyrogenic oxidation. That is why until and unless the safety arrangement is assured, the pyrogenic oxidation. So one should not do it, one should not go for the pyrogenic oxidation. Okay. The another technique is high pressure oxidation here, because
Sir, I can't hear you.
hello,
Hello?
hello, from which position, from which portion you have not heard me?
Sir, the silicon, after the silicon part.
Steam oxidation, have you heard this thing? Steam oxidation, what is steam oxidation?
Yes, sir, yes.
And
Yes, sir,
pyrogenic,
yes, sir.
the difference between steam and pyrogenic oxidation?
No, sir.
Okay, so the difference between steam and oxidation is uh, water vapor is used in this case. Now am I audible? Am I audible? Can you hear me?
Yes, sir, you are audible. Yes, sir, I can.
Mhm. Okay, now in this case vapor, water vapor is used, but here the gas is used in case of pyrogen. Okay, the reason is that water vapor there may be some contamination, but in case of if you use H2O molecule there will be uh, so in case of gas there will be no chance of contamination. Okay, so if you use H2O molecule, there is formation of the peats, because H2O when it will decompose, it will get oxygen on hydrogen, but if it is not as a molecule H2O, it can create some nucleation on the surface. Okay, so as a result of which there may be some defects. Okay, on the other hand, here in this case gases, so high purity gas of hydrogen or oxygen are used, and if you form it in steam high pure steam inside on the surface of the silicon wafer, then they will form both oxygen and H2O molecule, and they will form native silicon dioxide, and then uh, due to this growth rate will be faster and purity will be high compared to the H2O steam oxidation. Okay, uh, but one disadvantage of having this in case of pyrogenic oxidation here, these are used as a pure gas. Hmm? So handling of this hydrogen gas is very difficult, because we know that hydrogen burns itself, and if you use oxygen and hydrogen together to form H2O, there may be a chance of explosion. Okay, so there should not be any leak. You should take a precaution about it. After that, you can use this pyrogenic oxidation technique. Okay, you have properly assured the safety management, then you can go for the pyrogenic oxidation method. Okay, the next is high pressure oxidation. High pressure oxidation that can be wet and dry. Because in other the oxidation technique which I mentioned, that may be done at atmospheric pressure, but sometimes we need a high pressure oxidation because we need faster growth of oxide layer. Okay. So for faster growth of oxide, if you are if you increase the pressure inside the chamber, the growth rate will be faster, because over a small time you will get thicker oxide layer. Sometimes it is also required, but the quality of that oxide will not be as good as the dry oxidation, which is very slow. Okay, dry oxidation process is very slow. So in some cases we may not require very good quality oxide. Moderate quality oxide if you need, then you go for either steam oxidation or high pressure oxidation. For example, filling up groups for isolation technique, we may require say 7 micron or 5 micron of silicon dioxide. If you go for thermal oxidation in normal pressure, atmospheric pressure, it may take 2-3 days, maybe 50 hours, 60 hours, like that. Even then you may not get it. But if you go for the high pressure oxidation growth rate, high pressure oxidation, so growth rate will be very fast over a small time. You can get thicker oxide at high pressure. So these are the thermal oxidation: dry, wet, steam, and high pressure. There is another technique which is called halogenic oxidation. Okay, so here some halogenic material materials are used, that is chlorine, and that halogenic material will help to purify the oxide. Because in our system, if there is any alkaline element like sodium or potassium chloride, which is easily dissolved in water, so that the sodium and potassium ions contamination can be protected by using some chlorine um, incorporation into the chamber. So that is why in some cases the halogenic oxidation is also popular in case of mass grade high purity oxide growth. And these are basically thermal oxidation techniques you are growing. Another technique is called the anodization. And anodization is basically the process of extension of the electrolysis electrolysis process. Yeah, because their uh, cathode and anode inside the electrolytic cell, and if you take water and decompose the water will be H plus and OH minus. So OH minus will go towards the positive electrode anode, and uh, there the OH minus there with silicon, it will form SiOH. Okay, silicon hydroxide all twice. And SiOH, so you can see using this equations. Okay, so So OH minus will go towards the positive electrode anode, and the OH minus, there is silicon, it will form SiOH whole twice, and SiOH whole twice electron decompose with silicon dioxide and hydrogen. Okay. So that this is the electrolysis process. Basically, you need an electrolytic cell, and there you can deposit the silicon dioxide not grown from the native. That is the difference. Here in other technique, you are grown from the native silicon, but here anodization, your deposition was depositing the silicon dioxide as a molecule on the surface of the silicon. Okay. So here, first of all, the silicon dioxide, there is dry oxidation here, silicon plus oxygen. So SiO2, it's a dry oxidation. So after that, this H2O, H plus, OH minus. This OH minus is reacted with silicon, and it forms SiOH.
Voice is not clear. Hello?
Yes, yes, I can hear you.
Yes, sir. Okay, sir. Now I
I
can
can.
hear you.
Okay. Okay. So this, so first silicon and oxygen, it creates silicon dioxide, which is created by using dry oxidation format method. Then the H2O, this H2O, it is divided into H plus, OH minus. Then this OH minus is reacted with again silicon, and it forms SiOH whole twice. This SiOH whole twice again decompose, it will form silicon dioxide plus H2. Okay, this will evolve, and this will leave certain pores. So because you see in some H2O, again this one, this silicon again plus 2H2O, it gives Si to silicon dioxide plus 2H2 using wet oxidation. Okay, so so total reaction is silicon plus 2H2O will give you silicon dioxide plus 2H2. Okay, so this will evolve, and after evolving, it creates some pores. So, because you see, if some H2O molecules is there, obviously the hydrogen gas is to be evolved from the surface. Okay, so during reaction, if the hydrogen gas evolves, so then the problem is during the ejection process of the hydrogen gas, it will leave certain pores into the crystal. That pores means it can create some defects, pores into the crystal. So density of the silicon dioxide material will not be high if you go for steam oxidation, go for wet oxidation. But if you use only dry oxidation using oxygen, there is no residual gas, there is no formation of hydrogen. In that case, you can get very good quality silicon dioxide, and density will be very high with less pores. And those dry oxide, so dry oxidation technique is used in formation of the gate oxide in case of most, because there is you need very good quality of oxide. Okay, now here is certain things are shown. This is silicon, this is silicon, this is how the oxide is formed. So here either oxygen or H2 molecules are flowing here, oxygen or H2 molecules are flowing over the silicon. So obviously some of the gas molecules will come in contact with silicon, a silicon dioxide will form over this silicon. So when silicon dioxide is formed, then top layer will be the silicon, this layer. Then this oxidation species will not come in contact with the silicon. So those species uh, to diffuse to the silicon dioxide, and then it will come in at the interface. The reaction will take place, and then the silicon dioxide will grow. So as the thickness grows, the interface goes down. Thickness goes upward. The SiSiO2 interface goes down. This is one important parameter and an important factor also. At the same time, you can see, since after the growth of certain uh, thickness, the growth rate is controlled by the diffusion also. So it will be slowed down. Initially it will be fast. Initially, when there are no silicon dioxide, the reaction is controlled by surface reaction rate constant. But later on, when certain thickness of oxide is grown, then the growth rate is controlled by the diffusion phenomena. Because first, this oxidation species means either oxygen or hydrogen molecule will diffuse through the silicon dioxide. Then it will come in contact with the silicon interface. Then oxide will grow. So this is the growth mechanism. And now, since silicon and oxygen is combined to form SiO2, silicon dioxide, so thickness increases. If you see the volume and molecular weight of the oxygen and silicon, then it has been observed that 1 micron of silicon, if it converts into silicon dioxide, it will produce 2.22 micron of silicon dioxide. Okay, so the volume increases 1 micron of silicon. This 1 micron silicon will give you 2.22 micron of silicon dioxide. Okay. Okay, so I think that's all for today. Uh, is,
Okay, sir.
is this enough?
Yes, sir.
Okay, so that's all for today. Thank you, Srishti.
Thank you, sir.
Okay, see you on next week. Thank you.
Hello?
Yes, see you on next week. Thank you.
Okay, sir.
I will end.
Thank you.
End
Good
the
day.
class. Okay.
Okay.